Now I want to spend some time actually talking about dipoles themselves. Dipoles, the way we can define dipoles is that it's going to be, for us, it's going to be a system that has no net charge. So it's going to be a system that has multiple charges, but such that there's no net charge, but that charge has an asymmetric distribution within the system. So the kind of classic dipole is like what's drawn here. I've kind of drawn it vertically this time, where I have where if my system were this entire thing that I've boxed, then the box has no net charge, but the charge is configured such that there's positives down here and negatives up here. So I might draw this kind of like like a pill, right? That is plus E and negative E, perhaps, or plus Q and negative Q. And so then this field, these electric field lines you're seeing, is kind of the classic dipole electric field, where the field lines are kind of manifesting, some sort of bond between them. And why this is relevant, why this picture is relevant, is because many, many, many molecules essentially are very well approximated by this sort of dipole configuration. H2O is kind of probably the most famous example, where the idea with the H2O molecule is that I have oxygen and then my two hydrogen, that are separated by the 104.5 degrees. Chemists need to memorize that. I don't think we need to. But the idea is that there is a bond, and bonds are essentially, when I say a covalent bond, right, really all that means is that they're sharing electrons. So what goes on is that the oxygen atom, while it has 8 electrons, if you remember from high school chemistry, 2 of those are in an inner shell, and then 6 of them fill the second shell. But the second shell can have up to 8, and it's most stable when it has everything, when it has the entire shell filled. So oxygen by itself has these like 2 gaps in its outer shell that it would love to fill with electrons. So then oxygen essentially goes hunting for things that are willing to share electrons. And in this case, 2 individual hydrogen do the trick. So the individual hydrogen each have 1 electron that it kind of casually shares with the oxygen atom, such that essentially the electrons can kind of more or less fill up the oxygen shell, with the electrons kind of moving slightly away from the hydrogen as a result. So as a result, the charge distribution becomes it's not as uniform as it was when they were just individual atoms, such that the electrons are kind of gathering to fill the shell for oxygen. So there's kind of a negative net charge kind of at the top where the oxygen is, and then since the electrons from the hydrogen are kind of scooting their way towards oxygen, that leaves behind kind of a net positive charge for the hydrogen. And you can see how you might then kind of make the next kind of simplifying assumption where this is kind of more or less like this, the kind of classic dipole, which we will use for this class. And again, these kind of red things are optional or just notes to myself, essentially it's what I just were telling you, but not something I would ask you about. So these dipoles, again, they're exceptionally important. Essentially, probably the reason why chem majors have to take 2 semesters of physics, I would say, if I did make a guess. If anything, it's because you have some exposure to the physics of the dipole, which is what we're doing right now. Because we could just ask them. Dipoles, can do a variety of things and a lot of stuff in chemistry. So, and we're going to focus on symmetric dipoles. So these symmetric dipoles, where it's kind of plus E minus E or plus Q minus Q, they can either be permanent, like the H2O molecule, where the charge distribution is kind of permanently like this as a result of how the electrons kind of find their equilibrium. or it could be induced by kind of some external electric field. So the idea of the induced dipole is, right, if I have, say, a neutral atom, so there's some positive nucleus, and then there's the kind of electron cloud, which is negative, so I'll make it blue, and the nucleus red. Okay, so the electron cloud, the electrons are kind of symmetrically kind of just like hanging around the nucleus. But then if I throw a electric field everywhere, and maybe I'll have the electric field always pointing to the right, then we know the forces that are going to act on the electrons. The electrons are going to want to move against the field, where the nucleus might feel more compelled to go. That should have been blue, I'm sorry. I'm trying to cram it kind of small here too. So the electrons are going to feel a force, kind of against the field, where then the nucleus is going to want to go with the field, N for nucleus. So as a result, if the electric field is strong enough, that the neutral atom could end up being kind of lopsided, where, I'll really exaggerate it, in this case, where the electrons are going to want to, they'll still be attached to the nucleus, but they might kind of configure themselves to be a little bit more kind of lopsided to the left. And so in that case, then, you again get the dipole of kind of a plus and a minus. So that would be an example of kind of an induced dipole. Some quick definitions. We can define what's called the dipole moment as a vector that, and it mixes some units up. So essentially, there is some quantity, some vector quantity, that if we define this vector quantity, smartly, it's going to make our life a lot easier, in terms of quantitative things we might want to do down the line. And so experimentalists and chemists came up with this thing called the dipole moment, which your book uses P, so I'm sticking with that convention, where it is a vector that points from the negative charge to the positive charge. So note how I drew it that way. And has a magnitude that is equal to the, and again for symmetric, so if this is negative q, this is positive q, such that the vector itself is then just plus q multiplied by s, this vector s, where this vector s really is just the position from negative to positive, so it represents the distance between the two charges. S, so S points from negative to positive, has units of distance, right? It's the kind of inner dipole distance or separation. So in that case then, this is something that again points from negative to positive and is the value of Q multiplied by the distance between the two charges. So then if you think of units, what are then going to be the units of this dipole moment? Well, then it's going to be the unit of charge multiplied by the unit of distance. So the SI unit would be something like coulombs times meter. People have come up with their own unit. So this is often instead written with units called debye. So 1 debye turns out to be 3.34 times 10 to the minus 30 coulomb meters, or about 0.02 times the fundamental charge times 1 nanometer. And why these, it gets a little complicated because the debye is defined in terms of a different unit system that's not MKS, which is why then these numbers, when you convert to MKS, are kind of weird. But often it's used, this kind of debye is used. And the nice thing is that when you make that choice and change your units to be debye's, that typical molecule dipoles have values of this dipole moment that are somewhere between like 0 and 10, which is much nicer than say like 10 to the negative 30. So here's some values just to give you a sense. So if I have a proton and electron that are separated by an angstrom, or 10 to the minus 10 meters, so again I could draw that real quick. Right, so that's be some positive charge and then a negative charge, which in this case is plus E and minus E, and they are separated by 10 to the minus 10 meters. Well, that gives me everything I need to figure out the dipole moment, because then it's going to be the charge E multiplied by 10 to the minus 10 meters, and then it's going to be a vector that points, in this case it looks like, to the right. But this would be the magnitude, at least. And then when you convert it to have units of dBs, turns out that for this configuration, which might be like hydrogen, it's about 4.8 dBs. An isolated H2O molecule, it's about 2 dBs, or 1.9 dBs. If you have a bunch of H2O molecules on top of one another, then those dipole moments start interacting, for example. So when you have condensed H2O vapor or ice, the number can increase, right? So I put kind of an average value of 2.5. For ice, it might be a little bit higher, but so a few dBi. When you have something that's a symmetric molecule, like say O2, then there is no dipole moment, because again, there's no asymmetry, right? If this is O and this is O, and they're connected, then they're sharing electrons, but by the symmetry of the situation, essentially the electrons are symmetric around the two. So there's no one side that's positive and one side that's negative. So symmetric dipoles usually have, unless there's like a strong electric field or something that they're sitting in, and something gets induced, have 0 dBs. And then for like alkali metals and ionic bonds, where there really is a redistribution of electrons, it's not just that the electrons are kind of like being mutually casually shared, between the atoms, but that one atom essentially gets rid of its electrons and gives it to the other. Those create bigger asymmetries. If I take all of my electrons and just dump them onto another atom, then I'm going to be hella positive. Well, then that other atom might then have a very large negative charge, which then is going to give me a large dipole moment, because I'm going to have a very large, Q and negative Q as a result. So, and that's where you get up to like 10 values of 10. So like potassium chloride, potassium bromide have, a dipole moment of about 10 dBs. And again, what's going on is that, potassium is an alkali metal, which means that it has a very low electronegativity. So it essentially has an easy time when it forms these bonds, just giving its electrons away, which then creates a very highly polarized molecule. All right, so that's just some feel for the numbers, or some definitions. And these things are not just, something that we dream up to write chemistry exam questions, because these things are essentially, a dipole is essentially a metaphor for a molecule. And my chem teacher said that once. I really liked it. Because essentially, if you can understand the physics of the dipole, you more or less can understand, all the big ideas with molecules. Of course, the details, will depend on the exact molecule, and the details might be really important depending on what you are studying. But kind of the general, broad, zeroth order properties all come from this dipole. And this dipole moment essentially gives rise to a lot of the things that make dipoles, or molecules that have dipoles, really interesting. Like water, for example. Water has tons of remarkable properties, right? When you compare water to other molecules, water can, there's just so many things that are unique about water that it perhaps is unsurprising that water has played such an important role in the development of life. So, this dipole moment plays a role in, for example, why it has the specific heats it has, that it has a very high boiling point, so it can exist as liquid water, over a large range of temperatures. This dipole moment makes it a very effective solvent, because when you have a kind of little dipole moment, which then is creating, because again, I could go back to this picture, there's an electric field that is kind of surrounding the molecule, or surrounding the dipole. that electric field will interact with other charges. So it could interact with other things that have charge and essentially can hook onto things. And so that's why you get things like reverse photosynthesis as a way of like cleaning, using water as a solvent. This dipole moment also is what makes it opaque to infrared radiation. Essentially, infrared radiation gets absorbed by water very easily. That's why it's called a greenhouse gas. And also, that dipole moment plays a role, with these molecular bonds that form as a result, also make H2O very opaque to microwaves. And so it is then unsurprising why we call it a microwave, because it uses microwave radiation essentially to make water, essentially to dump energy into water, which is why in a microwave it's very easy to boil soup, because you just shoot microwaves and all the water molecules gobble up that radiation and then as a result gain that energy. But I could put a dry cracker in a microwave and nothing would happen, right? I could blast it with microwaves and it wouldn't really absorb them. So, so microwaves are essentially just, devices to heat up water. Why it has a high surface tension? Like if you ever tried to see, I had to do this in first grade, but we did not use the word surface tension, but we had to see which group could put the most drops of water on the top of a penny before it kind of tipped over. And water can hold a lot. So water, great thing. I had a friend in grad school at UC Berkeley where his PhD essentially was on some esoteric thing of water. So every day of his life, he just studies water, which, I don't know, to me, I would probably drown myself. A joke he did not appreciate. But again, given how important water is, and there's a lot of things to study, which is why chemists do. Another example, LCD monitors and displays. So if you have a liquid crystal display, what's going on there is that the liquid crystals, which I forget the composition, but these crystals all have little dipole moments that we'll see in the next section. These dipole moments tend to, if I have an external electric field, the dipole will try to align itself with the electric field. And so essentially for displays, you can tweak the local electric field at different locations on the screen, and that will make the crystals kind of orient themselves geometrically in different ways at different locations, which ends up changing, which kinds of light they let through or are opaque to. So essentially then you can use that to create an image. So your smartphone, again, dipoles are all the rave on your screen. Air filters, kind of talked about that above, right? An air filter, if you have an ionizing air filter, what that's doing is it's ionizing air molecules so that then they have a little dipole moment because there's more positive charge than negative charge if it strips it of an electron, for example. And then those dipole moments can interact with other like dust and stuff like that, and it can easily kind of attach itself and create bonds, with other particulates, which then can get kind of filtered out when they eventually flow back through the filter. Another example is sunglasses, right? Essentially, polarization is the result of dipoles. Essentially, polarization is when you have, a solid of dipoles, and all the dipoles are all aligned and in the same direction, for example. So, for example, if I have sunglasses where the dipoles are all oriented kind of vertically, then that means when a wave comes in, a vertical wave comes in, that the dipole essentially doesn't let it through. But then if I have kind of this horizontal wave, it essentially can pass right on by. So then if you have both of these come in, only one of them gets through, so some of the light doesn't make it through. The goal of sunglasses. So, dipoles. Good to know, good to love. So now let me briefly just conceptually work out that dipoles, what dipoles tend to do when they are within an external electric field. So So I'm not talking about the electric field that it creates. I'm not talking about this. But I'm saying I have a dipole and it's within some external electric field that is being created by something else. So in this case, I'm just going to use a uniform electric field that is pointing up, right? Just for demonstration purposes. Well, in this case, I could think about what forces are going to act on this dipole, which I could think of as 2 point charges, that are very close to one another. So I know for the positive charge, it's going to want to go in, it's going to feel a force rather that is in the same direction as the electric field. And then the negative charge is going to feel a force that is in the opposite direction of the electric field. So I guess it's, force on negative from this kind of E external, and on positive from E external. So in the case on the left, right, kind of the right side is being pushed up, and then the left side is being pushed down. Right, you could imagine, right, I could lay my pen on the ground, on the table, kind of oriented like this. Now I push one side of it up and the other side of it down. It rotates as a result. And then similarly, for the case on the right, if it's like that, then I know these are the forces it feels. And again, let's see, maybe I'll use purple. Right. So in both of these cases, the dipole is going to feel a tendency to want to rotate. Looks like counterclockwise as a result. So, and we described that if you think back to last semester, what this is saying is that dipoles experience torque. And a force that's applied, at some moment arm. We don't have to worry about the equations if you don't remember them. But the torques then result in rotations, which you can kind of conceptually visualize, hopefully, from this. So, just to, again, kind of remind us of the symbols. So, in this case, right, if I have an electric field that's pointing up, and I have my dipole, and here's my dipole moment. We're going to see why this was a good definition for the dipole moment. Then we just said above that it's going to feel a tendency to want to rotate counterclockwise. And you might remember that you can use the right-hand rule. That means that the torque it feels, it points out of the page, because I could take my right hand and point my thumb out of the page, and then my fingers curl in the counterclockwise direction. So if the torque is my thumb, my fingers curl in the direction of the resulting rotation. So, yes, still purple, please. Right, so there's going to be a tendency for it to rotate counterclockwise. So then imagine it kind of overshoots, right? So then it goes to the, it kind of starts like this and then goes to something like this. What happens then? Does it keep rotating counterclockwise, right? Does it start spinning? Well, you can think again about forces. Now it seems like the left is going to want to go up and the right is going to want to go down. So it looks like in this case then, once it kind of flips over to the other side, it's going to feel a tendency to rotate in the other direction. So in that case, we would say the torque points into the page, because then if I point my thumb into the page, my fingers curl in the clockwise direction. So, and then if you did formulas, though I don't know if you did cross products last semester, which we will do eventually, but there's that if you want it. So again, looking at these drawings, it seems like, oops, that meant to be a laser pointer. Seems like, this thing will rotate counterclockwise until it kind of swings over, and then it will kind of feel a desire to rotate in the other way. So it kind of seems like it's going to wobble back and forth as a result. And if there's something that, like a friction that might dampen it down, ultimately what happens is that the dipole aligns the dipole moment with the electric field. As you can kind of imagine, it kind of, just draw, it kind of starts here and goes here, kind of just goes back and forth between these two drawings. It just kind of wobbles, so that eventually what happens is that the dipole, which has a dipole moment that was pointing up, ends up being aligned with the external electric field. And again, that was pointing from the negative to the positive. Positive means it was red, and negative was blue, right? So essentially what happens here is that the dipole kind of aligns itself with the electric field as a result. If you want to be more explicit, we could say that the dipole moment P becomes parallel to E. And where this can create things like polarization forces, if you have, say, a large configuration of dipoles, maybe a solid or something like that, and if I throw an external electric field onto that solid or onto that kind of configuration of dipoles, then all of the individual little dipoles are going to align themselves with the electric field. And then as a result, you can just kind of look on this side. As a result, this side ends up having a lot of negative charge, where this side ends up having a lot of positive charge, where then in the middle it's kind of a wash. And that's just because these things, if all of these were kind of randomly, you pick a random direction, each one is in a different random direction, you could imagine they kind of cancel each other out. But when you when you make them all line up like this, then there's kind of a buildup of negative and a buildup of positive on the ends, which gives rise to, that's essentially what polarization forces are. So like van der Waals forces and stuff like that. These are all resulting from these sorts of interactions, these dipole moment interactions. Okay. I'm going to end. That was just a lot of concepts about the dipole, and I want to do one more kind of math calculation for lecture C.